let's go through the definition that I like to use, and I'll explain why. I like this definition because it says that AI is essentially something based on what we expect human behavior to be in a given situation. And the interesting thing about that is that changes over time, right? 20 years ago, we would not have ever thought that maybe a car could maybe drive itself. Now it can, things like that. 20 years ago, we probably would have not thought that we could text people around the world, but we can. So things change over time. Now, there are many ways to implement AI, but one of the most common is through something called machine learning. And this is the definition I like of machine learning. The good part about this is that the data-driven, focus in on that. If nothing else, remember that all we're going to do today is data-driven versus you writing program instructions. And by program instructions, I mean if your boss came to you and said, you know, we need to build this application, you would probably write a bunch of if statements, case statements, all sorts of logic. Now you're going to go back to him and say, just give me the data and I'll have the computer do it for you. At least we hope so. Okay, and what that does though, from the data we can learn so much more than we can as humans because the answers are in the data. We can do things like this. Suppose I have this picture, and in this picture, the machine learning model can go ahead and detect that there is a boy and some tulips. Even more so, because it understands the relationships that it sees in the pictures, it can generate a caption of the action occurring in that picture. We can also, if we had a restaurant, maybe that we would have reviews and we'd want to put up the best or latest reviews on the site, we might take this review and say, hey, this looks really, really good if we were coding it. You know, the keyword love was in there and great and all that good stuff. But maybe not, huh? We can figure out or have the machine learning system figure out the sentiment within that review and not put it up on the main page. And then there's the one that we see all the time. I happen to live 15 miles from Tesla. Teslas are as common as Toyotas are here in Malaysia by me. And a lot of times you see people half asleep or not really paying attention, but luckily their car is checking for them. So before they make a change to the right lane, it looks and makes sure the lane is clear. Okay, so let's talk about a little bit how we learn. Suppose I were to give you these two images. Oh, my clicker's having problems. What's that? Anybody? Cat, right? You guys are 100% accurate. How about this? Dog. How did you decide that? Anyone? No, but what told you that was a cat versus a dog, if I give you those two? Experience, yeah. And through experience, you maybe learn that, you know, there's little pointy ears and things like that on a cat. Of course, Doberman Pinschers have pointy ears. But it has a small nose, and maybe most significantly, those kind of cat-shaped pupils, right? And over here, we have a dog, and he's got a long nose, and he's got those round pupils, right? But can you see his pupil? How do you know he has a round pupil? As other people said, by experience. You've seen a lot of cats and dogs. Okay. But let's make this just a little bit harder. How about this? This is the famous in machine learning Muffin and Chihuahua test. This is from a lady named Karen Zeck, who's a graphic artist in Portland, Oregon. And if you go to her Twitter feed, Teeny Biscuit, I believe it is, you'll see examples like this. And let's focus on the one in the center. Now, you can say, you know, just like we did with the dog and the cat, right? Dogs have two eyes, and a Chihuahua has two black eyes. Oh wait, the muffin looks like it has two black eyes. Below the black eyes, there's a black nose. Oh, no. Got a black nose on the muffin too. And how about that little smile that we know all Chihuahuas have? Darn! Okay, so maybe it isn't quite so easy when we have something we don't know about and we haven't seen over and over again. So the question is, how do we learn this? Where would we go for inspiration on how to learn that? Well, maybe to this. Anybody know what that is? Neuron, right? Anybody know how many you have in your head? A lot? 10, 15, 20, something like that? No, something on the order of 100 billion of those are in each of our heads. Some that I've met, fewer than other people, but we'll leave it at that. The good thing to note is over here, let's see if this laser pointer, I'm going to point to this screen, so you guys got to look it over there. We have in the center, we have kind of this central neuron, and the important thing is that we have interconnections between this neuron and other neurons. So along these interconnections, we can get signals from other neurons, and that's called firing the neuron from the other neurons. And our neuron then here in the center will figure out, gee, does those firings from that other neuron rise to the threshold where I'm going to myself fire another, I'm going to propagate the signal. And if it does, it will then propagate it, let's say, on this branch to another neuron, on that one to another one, and so on. So this is kind of an interesting structure, and as one data scientist studied in the 50s and 60s, and came up with the artificial neuron, which looks something like this. Pretty similar, right? We've got inputs coming in from someplace, be these pixels in a display or other neurons or what have you not. Some magic processing goes on in the center, and we output. Now, obviously we're not sending electrical chemical signals in an artificial neuron. We're sending math. Just mathematical values are transiting across these, okay? So let's open it up and see what's in there. Hello, there we go. Okay, what we have here is we have our input, and if you read this equation, you'll see that each one of the input gets a weight. And that just says how much attention am I going to pay to the input, this particular input. If it's a big number, we pay a lot of attention. If it's a small number, we don't pay that much attention to it. And then there's a little bias offset number here too. But the big thing to remember is that these weights are something we can train by exposure to data. If we show it 10,000 pictures of dogs and 10,000 pictures of cats, what it'll learn are the pattern of weights that identify a dog and the patterns of weights that identify a cat. All right, moving on. But don't get hung up on this. I mean, it's really just a little multiplication and addition, right? Nothing you haven't done since probably grade school, hopefully, right? Tell me, you guys really did. Now notice this here. Who took beyond grade school math and took something like geometry in later school? Pretty much everybody, probably, somewhere in there. Do you remember an equation that said y equals mx plus b? What does that draw? Straight line. So there's a small problem with this. This is essentially y equals mx plus b. And what that's saying is the firing of data going through here must fit along a straight line. What if our data is not linearly scaled? In other words, just a little bit more doesn't just push it a little bit more. Maybe it scales at the square or the cube or something else. Well, we have a problem. So to get around that, we introduce something called an activation function that just deals with the nonlinearity. But the key thing to remember is we're just summing all these weights and multiplying them and adding them all up. Questions? Any questions on that? Straightforward? Cool. And that is the major amount of math we will learn today, folks. Okay, and there's the equation. But once again, they look mostly like this, or more appropriately, because just like our brain, we want to put them together with other neurons, we put them into this neural network. On the left-hand side, we have inputs. And these inputs could be a database output, maybe a row in a database that says, how much a person makes, how much debt they have, and things like that. And what we're trying to determine on the output is whether we should give them a loan. Or it could be pixels in an image, like a muffin or a chihuahua image, maybe. And what we're trying to do is push this through this network and figure out, is that a chihuahua or a muffin or a dog or a cat? In between, we have these things called hidden layers. And I put the parenthesis S there because there can be many. We're going to be playing around with a neural network that was pre-trained for us that has several hundred of those hidden layers, and each one of those layers has several thousand neurons. So there's a lot of mathematics or addition and subtraction or addition and multiplication going on, but it's just a bunch of addition and multiplication. Okay, so let's see how this works. How do we train it to recognize like a dog or a cat? Over on the left-hand side, we see we have some images. Now, I've just driven 4, but in reality, if you were training this model, you would have maybe 40,000 or 50,000 images. And that would be easy to get today, right? Because we know we can go to Google and get a whole bunch of dog images, and we know that everything else on the internet is cat images. So this is going to be really easy to get these images. Okay. So we have our network, and we're going to initialize the values to some random number. We're just going to run some sort of random function. We've got to give all those weights and things like that values. So we're just going to initialize them to random values. And then we're going to take the pixels of that, of that first image and move them forward from the image into the first layer, and eventually through the second layer, and we're going to come out with the probability that that's a dog or a cat. Is that a good result? Okay. So we're saying 25% dog, 75% cat. Are we surprised at that, given that I just sort of randomly initialized those, right? We shouldn't be. It's just random values. Okay. So to fix that, we use something called backpropagation. And the way that backpropagation works is it takes a look over here and says, I know that was a dog picture. I've got to make an adjustment. So I'm going to adjust that first weight over there. And now it's going to work backwards from the classes we said it was, a dog or a cat, back to the left of that image. Makes that adjustment first to that value, and then we'll make adjustments out to those values. And this gets repeated for a whole series of data. Remember I said we might have 20,000, let's say 50,000 cat and dog pictures. We're just going to keep passing them through them and adjusting them. We may even cycle through our 50,000 20 or 30 times. So it's 20 or 30 times 50,000 images pushed through this thing and these adjustments made. Eventually, so maybe 20% of the way through all that data, we run into this cat image. And when we push it in, it says it's a cat. 52% cat, 48% dog. Is that good enough? No. That's, we're getting there, right? We're getting better and better, but we're not there yet, right? But we really, really want a strong signal. I mean, I want to see like 99% cat. I don't know about you guys, or 1% dog. So, what do? Backpropagate again, forward propagate, over and over and over. That just means we needed to train longer. Do it again. And now we get to the point where our model is trained. So if we were to look at the performance of the model, it's going up and up and up, and it just sort of plateaued. And then we'll declare it's trained. And now when we have our trained model, we can deploy it somewhere. And then if we take an arbitrary cat picture, like that one, we should see a very, very strong signal that that's a cat. So that's how we train our neural network. Okay. This particular form of algorithms is old. You may have seen it before. It was originally developed in the 1950s and 60s and so on. So why are we just hearing about machine learning in the last 7, 8, 9 years? Well, there's a small problem. Oh, let me back up. Or a couple of problems. One, data. In the 1950s, if I would have said, hey, you're my intern, go run out and get me 50,000 photographs of dogs and 50,000 photographs of cats, and then convert all the data to bits, because I just want to look at the pixel values. He would have said, pixel? What is that? Right? They couldn't do it. They didn't have the technology. Second, they didn't have the data. As an eye test, you guys can try to read the legends, but you can just look at the general shape of the curve here and note that as we've gone on, we've gotten more and more data. Again, thanks to Google, cell phones, and cat images. Because, you know, cats are like 90% of that data right out in the internet. We know that. Okay. And then to process that data, we need a little help too. Does this look like anybody in this room? I bet more than a few. Gamers. Thanks to gamers, we have high-performance GPUs in just about everything. Your phone has a GPU that's more powerful than a GPU was in a high-end graphics processing system used by, you know, like Pixar or somebody like that 10 years ago. Just think about that for a second. Your phone is more powerful. They would have killed for that power. And this guy maybe will kill for that power. Okay, so that's why in about 2012 you started hearing about machine learning, neural networks, and what have you not. It just started becoming out there. And on tests like identifying from a bunch of photographs which is a cat and which is a dog, they started actually beating hand-coded human, you know, programs that people wrote. Okay. So where does this get us with Angular then? Well, we had these big servers. We could build these models. We can always wrap one of these models in a service, right? Make an HTTP request and have it go classify our dog or cat image. That'd be the model that you created, or maybe one you buy. If you're not familiar, Amazon, Microsoft, and Google will sell you pre-trained models that have been trained for you, and you can just include in your Angular applications. But they're server-side, so there are some issues, right? There's cost. Those companies are going to charge you so much per call or what have you not, or thousands of calls. If you run your own server, there's cost of maintaining that and that sort of thing. The other thing is the data has to go back and forth to servers. So there's a latency problem and, more importantly these days, a security problem. How many of you guys develop websites and have ever had your boss say, we have a security issue? That's the beginning to a really bad day, or week, or month, or whatever. So this is becoming a real big problem. So why don't we do machine learning on the web? That cures a lot of things, right? If we do image recognition and things like that, we'll just say, yeah, it's a dog or something like that, not the pictures of it, or if it's a person, this is Bob or Sue or whoever this is, and not necessarily ship their image across the web where somebody can intercept it. So, how do we do that? Or, more, how do we do it now? What's happened in the last few years is our frontline browsers, such as Firefox and Chrome, now support WebGL. Are you guys familiar with that? WebGL is a math library, an accelerated library that lets us get to the graphics processors on our desktop or laptop machines. And there are frameworks, and the one we're going to talk about today is something called TensorFlow.js. Has anybody ever heard of TensorFlow? Yeah, okay. Let's talk about TensorFlow.js. This is actually started as kind of a side project. At Google, they give you like 20% of your time to play around with projects. And these two guys that I know, Nikhil and I forget the other guy's name, started this. So they essentially said, you know, we really want to do stuff in the browser because of all those things we talked about. So we're going to take the TensorFlow code and rewrite it completely in JavaScript. Literally. There is no like it's calling out to some C++ routine or anything. It is written in JavaScript there. And that's good. Why do we like that? As a web developer, that means you can include it just like any other JavaScript library, right? So, and then we can get access to those client GPUs. We have a couple of options when we deploy a solution using this technology. One, we can use pre-trained models. That could be models you built. Or it could be models somebody else on the internet provides, and you just pull down to your application that you run inside Angular on the browser. Second, some of those pre-trained models are written in such a way that we can go in and retrain them. So if we have a class of objects, such as our orangutan here, which I keep calling a monkey, but orangutan, we can retrain it to recognize those. Oh. And finally, you can create and train models from scratch on the browser using TensorFlow.js. It's not going to be as performant or as fast as doing it in a server, but you can do it. And today, we're going to take a look at a little demo with running a pre-trained model that I'm going to bring down to my laptop. And I have a little webcam you can see right here, and it's going to see what you guys are. All right. This model that we got is this one here right in the center. It says CocoSSD. It's a variant of the models supported in there. And if this URL, if you're interested in playing around with these, you might want to take a picture of that or go there. And they have a wide range of models that you can play with. Okay. This is built off an article I found from Erdem, who is a developer out of Turkey, an Angular developer out of Turkey. And we've modified it to do what we want. So, what can we build then? Let me get back to the Johnny. Get this in my hand. This will be easier. Okay. Well, maybe cool things, right? This guy's having a great time. Games that learn and teach, those are real common. You know, you can build those. It's great for your portfolio, too, if you're thinking about moving on to another job. Next-gen social media. As we know, social media today has a slight problem with bias and things like that, right? Just slight. Maybe you can cure that. And then news validation. I'm from the United States. We kind of have this problem with certain of our, well, anyway, we have issues with news validation in the United States. And, and of course, new entertainment. Nobody has ever taken a technology and not built something that people will spend money for to use their time. Okay, disease prevention. People are building models to detect really serious diseases, life-threatening diseases, or like blindness, like macular degeneration, which is very prevalent. And then new medicines and treatments. My daughter does this as a cancer research using machine learning. And then, of course, powerful assistants. But let's just move on to one, because we're running out of time. Anybody ever use Airbnb? Airbnb now requires you to put up a picture. If it asked you for a picture, what would be the first thing you'd reach for? Maybe what you had in your pocket, like your ID, that might have your driver's license or something, it'd have your home address and things like that. Airbnb does not want that. And, I guess you can't see it because it's too grayed out there. But essentially it says, hey, this is some government-issued ID. We don't want a government ID because of security. The last thing Airbnb wants to do is be the guy that told somebody you were going to be out of your house, and oh, by the way, here's your address. So go ahead and go rob that guy. So yeah, they definitely don't want that. Okay, just to finish up then, here are some references that are cool. TensorFlow.org, JS, and then the models we saw. And if you want to, you can even pull down the source code for TensorFlow JS. It's all written in TypeScript, mostly. There's just a teeny weeny bit of raw JavaScript, but it's mostly written in TypeScript. And with that, thank you very much.